So welcome everyone. I think we have a great 2 days planned. On behalf of the principal organizers of this meeting, myself and Rahul and Sid and Saram, I'd like to welcome everyone. I think it's going to be very, very stimulating. It's rare that me personally I get to go to a workshop that is completely dedicated to the number one thing I'm most interested in. I'd also like to thank Andy Millis, who's been excited by this idea of putting this workshop in from the very beginning, and the rest of the staff and principals at Flatiron Institute and Simons and CCQ. I'm going to start off with just some very introductory remarks and some ideas, as well as kind of setting the context of what we hope is going to happen here in the next 2 days. And the idea behind this conference, I think one can say, is that it comes from the idea that I think it's fair to say that many problems that are at the forefront of modern condensed matter physics can be characterized what's called quantum correlations that are invisible, or let's say imperfectly characterized by conventional spectroscopic techniques, which are typically based on linear response. And there's been a number of recent developments, experimental and theoretical in this regard, many of them, of course, by people that are in the room. And these developments give indication that nonlinear spectroscopies, or in some cases non-equilibrium spectroscopic probes of materials, may give a wholly new classes of information about many of the things that we're interested in. So it's of course true that aspects of nonlinear spectroscopy it's an old subject, but many of the aspects of it as applied to many body systems, I think it's fair to say this is a subject which is really in its infancy. So the idea here is to bring together some group of people who talk to each other, to see what's been done, to think about what's interesting, work towards developing a shared language in which we can think about how to propose and solve interesting problems. The meeting is for experimentalists to educate theorists on the kinds of work that's ongoing now and the kinds of experiments that can actually be done. But it's also for theorists to educate experimentalists on what they think is interesting as well. Conference is a mix of people who've done experiments, worked on various aspects of theory, on superconductors, magnets, topological systems, and there's already a huge world of nonlinear optics and people working and applying nonlinear probes to chemical systems and few body systems. And so the notion that aspects of this, any of this is new, may come as some kind of news, but we hope to be developing some new approaches. So I want to start with just some kind of basic comments to kind of set the page. Any dynamic driven system can have nonlinearities, and of course light matter interaction is no different. Nonlinearities in physical systems are often unwanted sources of complication, and there's of course a reason we like linear response. It's the simplest, and in many situations it's very powerful. But nonlinearities can be an interesting source of phenomena, and they can be an interesting source of information, important probes of materials. Typically, when we think about nonlinear phenomena in solids, we think about some kind of perturbative approach, and there are different kinds of processes, and we'll make perhaps reference to some of these throughout the workshop. They're probes of different things, and so perhaps second harmonic generation is perhaps the most famous as a probe of solids that gives different information. In dipole approximation, the second harmonic response is only possible if you break inversion symmetry. So in the application to the subject of quantum materials, probably the most prominent application of nonlinear spectroscopies has been to materials that break inversion symmetry in some fashion. So other probes of structure, for instance, things like X-ray diffraction, can be very, very insensitive to, let's say, small changes and subtle changes in structure that, say, for instance, due to oxygen, the position of oxygen atoms, that second harmonic generation has been very adept picking up. As I mentioned, the topic of second harmonic or nonlinear optics and higher harmonic generation. This is, of course, a very old subject with an August history. And this was first seen in this famous paper, or if you say not seen, if you will, by this famous paper of Franken et al. From the University of Michigan. This paper came shortly after the invention of the ruby laser. So the intensities necessary for this experiment were made possible by invention of the laser. And this work, they sent wavelength of 694 nanometer light through quarks, and set the output light through a spectrometer, recording the spectrum, which indicated the production of light at 347 nanometers. And you can read what they say here. The arrow at 347.2 angstroms indicates the small but dense image provided by the second harmonic generation. So you see where the arrow is. There's nothing there. And this was famously, when published in PRL, the copy editor mistook the dim spot of light at 347 nanometers as a photographic paper. It's a speck of dirt, and removed it. So it appears in the corrected version. Hopefully we can do better than this nowadays. It's used routinely now, of course. Higher harmonic generation is the second harmonics, but we will go up to hundreds of harmonics have been seen. And this has become a kind of a routine tool now to characterize various aspects of semiconductors. Okay. So even more recently, higher harmonic generation has been used to characterize materials that we might kind of imperfectly characterize as quantum materials. And that's what the workshop is about today. My own kind of journey in this regard actually began with me reading this paper from Steve Cundiff, who's here, which appeared in Physics Today some years ago. This nice review now by Steve Cundiff and Shaul Mukamel. I read through this 5 or 6 page introduction to the topic written for non-experts, and I had absolutely no idea what they were talking about. I recognized it as something perhaps potentially interesting, but I think it shows one of the barriers to this field is that there's very often different languages from different groups of communities talking about the same thing that is rendered in a fashion which can make it rather opaque. So it took me many years of kind of iterating between different papers and groups to actually even be able to kind of parse this. One of the topics that we're going to hear quite a little bit about is multidimensional spectroscopy, which in its simplest form is two-dimensional coherent spectroscopy. And Lara and I have had discussions even as of last night about to what extent this is a good representation, even at a cartoon level, of what's going on. I find it useful, but the notion basically is that imagine you have 2 weakly anharmonic oscillators. We could think of them as charged pendula that we might drive with electric fields. And if they're independent charged pendula, we can imagine creating some kind of generalized spectrum of where we're going to pump at one frequency and probe with the other, applying a protocol which perhaps has this particular form here, where we might use a pulse and a B pulse and look at the response when we look at both pulses together, subtracting off one pulse by itself and the other pulse by itself. And by definition, the thing that comes out is the nonlinear response, and plotting that nonlinear response out of the page. And if this was the particular physical situation, you would get these 2 guys on the diagonal. Now, if you introduce some kind of small coupling to them, if you were doing an experiment in linear response, what would you see? You would see perhaps some shifting of the peaks. You would see some broadening, maybe asymmetries in some fashion. If you had good enough theory, you might be able to create some story out of that, but one never has good enough theory, and you wouldn't really be able to understand exactly what's going on. But in the nonlinear 2D response, you get these off-diagonal peaks. So it's not a matter of small subtleties, it's a matter of peaks being there or not there. So that's one possibility. And so we're going to get some examples in the workshop where just exactly this kind of thing is going on. Another possibility, and one that we've used in my lab in 2-dimensional spectroscopy, is basically trying to separate out the effects of homogeneous and inhomogeneous broadening. This is one of the main things that this kind of spectroscopy can be used for. You can imagine if you have many oscillators, let's say, which would congest some frequency access, then very roughly speaking, let's say the projection of the nonlinear response into either direction looks like the linear response. And so you get this big broad blob here. these oscillators may be very well defined in frequency, but you can't resolve them because of this inhomogeneous broadening effect. But you can imagine, for instance, taking this kind of anti-diagonal cut, if you will, and being able to see what's the intrinsic length. Now, we're going to hear Steve, who wrote this article, which was important for me, is here. We're going to hear about what's going on with multidimensional spectroscopy nowadays. And this is indeed a technique which has been used to great success in looking at things like quantum dots and now excitons. It's made big impacts in the physical chemistry world. For many of us interested in material systems which exhibit their prominent effects at low temperatures, things like superconductors and magnets, various kinds of interacting systems, the energy scales are small. And so what made it was also part of my thinking that this was a promising area was the work from Elsasier's group, who is there, and these individuals who, this is one of their early papers where they showed that they could do terahertz two-dimensional coherent spectroscopy. So now 1 terahertz is about 4 millieV, which corresponds to tens of degrees Kelvin. And so you're on energy scales, which are kind of relevant for the low temperature, low energy effects that we're interested in. I don't know if it's true or not, but I like to think that some of the modern interest in this topic came with this. So I got interested in this and was blathering to various theorists about this for years. I think Sid was one of the ones who I was first telling that I thought this was a really interesting thing to do, to apply to spin liquid systems. And so eventually a former student of my colleague, Oleg Chernyshov, took me up on this idea. And we wrote this paper some years ago, which we hope to, it's kind of rather straightforward once you understand what we did, but it's a 4-page PRL with a 45-page supplemental, because we wanted to kind of set out the language about what's important and how these experiments might work and how they could possibly be useful. So I like to think that some of the modern interest in this topic came from getting the attention of people interested in systems like spin liquids and applying it to, which is perhaps the model, the simplest model version where you have fractionalization. And so this was some years ago, the Ising model in transverse field. I don't want to talk about that too much. Let me just say a few quick other things. One thing we're not going to have at this meeting, but I think is potentially interesting, and so I just wanted to mention it, is the use of these techniques to look at metals. So these nonlinear terahertz techniques to look at metals. I'm happy to talk more about this. This is me just kind of throwing in here just something that you already know, that if we have, let's say, a normal Fermi surface that we might displace in some fashion with an electric field, our normal linear conductivity measured, let's say, with DC, sensitive to it in DC transport, but explicitly what we would measure in a linear response optical conductivity experiment, if you have some kind of Drude peak, is the rate that this circle returns back to the origin. But one could imagine other kinds of distortions you could make to the Fermi surface. And through doing polarized experiments, I believe that this is possible. You can measure these, and the kind of the most obvious one would be if you kind of come in with if we call that one I just showed you, the E1U relaxation. A possibility is that you could kind of come in and excite a system in some fashion, and everywhere, if you will, excite quasi-particles around the Fermi surface, and then watch them decay. And this is going back to a low energy state. And so it's sensitive to a particular class of scatterings that remove energy from the electronic system. So electron-electron scattering, even if it's strong, isn't going to do that. And so generally you have to couple to some kind of other bath. So this gives you a kind of a diagnostic on what some class of scattering events. One that I think is going to be particularly important, and this is kind of a poor cartoon, but hopefully you get the idea of it. You've come in with, say, a pulse, which two pulses, which say has a strength E squared, and then has at least a projection on the cosine 2 theta as you go around the Fermi surface. That's the perturbation. And you can look to see how this kind of thing relaxes. And so this is something that we're doing in my group now. We're not going to talk about it at this meeting, but this would be characterizing the gamma B1G response. And this is some ideas related to this is something that Mark at Sherwin had worked on years ago with looking at relaxation in narrow gap semiconductors, right? The A1G response anyway. So this is, I think there was theory in actually the late 60s on this, Boltzmann transport treatments of how does relaxation work and non-parabolic. There the consideration was semimetals, or semiconductors, but I think it's something that is worth looking at in kind of a more modern context. So just finally, there's a number of different things that I think are interesting here, and this is by no means some exhaustive list of the different things, and I have the various speakers of the workshop I've kind of thrown in at various points, rather probably imperfectly characterizing them, but some of these I've mentioned. Why is nonlinear spectroscopy for many body systems? Why should we do this? It's complicated. It's more technically challenging, both experimentally and theoretically. So we better have good reasons. And the good reasons shouldn't just be that it's hard. We want to actually have something that comes out. There's a real new information about physical systems that we're interested in. And some of these I've mentioned. So distinguishing homogeneous and inhomogeneous broadening in real and momentum space. And so some of the individuals that very roughly, I think, might talk about some of these things. The notion that that there's inhomogeneous broadening that can happen in momentum space. This is a kind of perhaps a poor characterization of what you might consider happening in a spin liquid system where you might make two spin-on pairs. We're going to hear about the possibilities where you have different, one of the advantages of nonlinear spectroscopies is that you have different excitation pathways to make some particular excited state. And so there can be interference between these, and some particular excitation pathways can enhance certain processes or excitations that you might not see otherwise. And we're going to hear a little bit about that from these individuals. Excitations that might be forbidden in linear response and dipole approximation. I think this is a very interesting thing. There hasn't been a whole lot of work here so far, but there's a lot of interest in the world of quantum materials in higher hidden order states, multipolar orders, and these have elementary excitations which may carry, let's say, angular momentum that is not accessible in the normal, say, dipole approximation scheme. And so nonlinear responses may be important there. Sensitivity to, and I put in quotes, quantum correlations, to kind of abuse some language, which is invisible, excuse me, at the level of linear response. And so, for instance, things like Berry phase and higher order correlation functions are things that we might be able to see with nonlinear spectroscopies. There's been a lot of work and interest in recent years about various kinds of transient states or non-equilibrium states. And so we're going to hear about that as well. And if a state is transient, then of course you need to use some kind of ultra-fast probe of that. We're going to hear about relaxation rates in various conducting systems from Dmitry Basov, and this in particular here about nanoscale systems and the probes thereof. And then coming back to one of the the original thoughts about multidimensional spectroscopy, it's useful to look at small nonlinear couplings between what you might consider to be the elementary excitations of systems. And so that's something which is also very important. So I think it's going to be an interesting workshop. I think I'll finish there. At the end, on Friday afternoon, Rahul is going to give an overview of things that he thought was interesting. But if there are things that participants think are particularly compelling areas, either things that weren't addressed at the workshop in the general topic, or things that came up that you want to be emphasized, bring them to Rahul's attention, and he can kind of highlight them as being grist for the mill of further discussions after the workshop's over. So I'm happy to take questions, and otherwise then we'll just kind of get started.
I'll just make a comment that in case there's any conspiracy theorists in the room, I have seen the original slide, and the dot is there for the second harmonic.
Oh, the original slide.
The original slide.
Okay, good. Yeah. Yeah. Well, we lots of records recently of people claiming something was there in their data and it wasn't. So it's important we go to the
exactly. It's in the archives at University of Michigan in case anybody really wants to verify it. But I've seen it. So.
Okay. Well, you may be in on the fix, so we don't know.
Was there a fix? Did they publish the errata?
There's an errata.
No, they didn't.
Oh, there's. I thought there was an errata.
Yeah.
And you can't check now because the fourth author on that, Alan Hill, who did the experiments, just died last year. So it's all.
Right. So Steve Cundiff's our only conduit to the truth, as usual. Yeah, Andrea.
I mean, I'm just going to declare one of the things that I would like to understand in this conference the next 2 days is whether multidimensional, in absence of a resonance, is worth anything. And I'm not talking about a inhomogeneously broadened spectrum where you can burn a hole and find a resonance, but if you have a continuum, that's really,
In the absence of a, do you mean
in the absence of one resonance, hold on, some,
but with not inhomogeneous, what are you
no,
distinguishing?
no. Let's say when you said, I want to understand how a metal works.
Yeah.
Does multidimensional give me any information beyond a pump probe?
I have some thoughts on that. I think
That's right. So, I'm sure I would like to learn about that. And understand this.
That's a good question.